This is a great question. We're trying to find how many different ways can this diagram be completed. Now, you might manage to fill the grid successfully, but that does not help you actually work out how many ways are possible because maybe there's some that you've missed. So we need to do this very carefully. The first thing I'm going to do is add up the numbers from 1 to 12. Now, when you add up the numbers from 1 to n, there's actually a nice formula, a half n plus 1. This is a formula for the triangle numbers. So here it becomes a half times 12 times 13, which is 6 times 13, which is 78. Okay, I'll bring that back in a minute. Because when you have this sort of question, the way to go about it is to look at the numbers along each edge and then account for the fact that we're going to be, well, we could add all of these up and then it must be divisible by 4. But to be able to work out what they add up to along one edge, we can add them all up and then divide by 4. And here's the thing, if I add them all up, then I'm going to get my 78 because I know that I'm including every single number. But I'm going to double count the ones in the corners. This 6, for example, is counted when I do this edge, but also from this edge. So I should say the sum of the 4, I don't know whether to call it edges, yeah, edges or lines, is going to equal 78 plus 6, because it's counted a second time, plus 12, plus 5, plus this missing one, which I'm going to call x. 78 plus 12, that's a good one to start with. That gives 90. Then plus 11 gives 101 plus x. So this must be divisible by 4, so that each edge adds to the same thing. And therefore x will equal 3 to give 104. Remember, it's the last two digits we need to be divisible by 4, or 7, or 11. Those are the only numbers in our little set. Now we've already used 3, so I can ignore this one and just focus on 7 and 11. This idea that I've just done is like so important for questions like this. You know, it just immediately reduces all of our grids to 7 and 11. And so we can ignore all the many other numbers that would go at the top. And from that, we'll be able to start working out the other missing numbers. It just kind of all starts coming together. So let's first of all look at x equaling 7. So I'm going to put 7 there. Now remember, we had 101 plus x as the total. So I'm going to get 101 plus 7 divided by 4. That's 108 divided by 4, which gives 20. What is it? 4s into 10 go 4s into 108 go 2, so 27. Okay, I've got 15 already. Now to get to 27, I'd need to have 12, but I've already used 12, so this is not possible. Okay, I've already ruled out one of them. We're left with x equal to 11. So for this one, it's 101 plus 11 divided by 4, which is 112 divided by 4. In fact, it's the next one up from 27. It's going to be 28. And now this is 11. All right, let's try and fill this grid. So over here, I've got 19, which means that this must be 9. And then let's focus on the remaining pairs along the edges. So over here, I've got 17, which means that this total will have to add to 11. Here I've got 17, so this total will have to add to 11. And here I've got 18, so this total will have to add to 10. And let's just write down the numbers that we've got left to use. We've got 1, 2, 4, 7, 8, and 10. Now there's only one way here that I can get 10. 2 and 8. So I'm going to have to put 2 and 8 in some order here. Okay, we'll come back to that. We're going to be timesing by 2 to account for the fact that we could swap them around. Then to get 11, we've got 4 and 7. They go together, and 1 and 10. But I could choose to put them here or here. So I've got one way to put the 10, and then I've actually got two ways that I can put the first 11. So I could put the 4 and the 7 at the top, or I could put it at the bottom. And then I'll have one way to put the second 11. It will just, it will just have to go where in the remaining spaces. Now, for my 10, like I said before, we can swap the 2 and the 8 around. So for every configuration I have here so far with 2, 4 and 7 and 1 and 10 in some way, we can swap the 2 and the 8 around. So I'm going to times by 2 again. This accounts for the 2 and the 8 ordering. But I can then do that with 4 and 7. For every ordering that I have, I can just swap the 4 and the 7 around, so give another 2 options. And then finally, there's going to be another 2 options from the 10 and the 1. So we've managed to show that a grid exists. We've got these totals, 11, 11, and 10. I've written down the ways that it can be made, but the two 11s can be swapped, which is what gave rise to that. Within each little pairing, we can then swap them around, which is what gives rise to further arrangements. This is the idea behind the product rule of counting. So I'm assuming you're familiar with this, and therefore we can just times these together, giving 16 possible grids. I'll just fill one of them to demonstrate what I mean. So the 10, yeah, we could put the 2 and the 8 in, and then I could put the 4 and the 7 here, and the 1 and the 10 here. But of course, I could swap these two around. That would be a new configuration. Or within a given configuration, I could swap the 10 and the 1 around and keep the 4 and the 7 the same. Or I could swap the 10 and the 1 around and then swap the 4 and the 7 around and then swap the 2 and the 8 around. So there's all these different things we could do, which is what I've encapsulated with this multiplication here. Well done on your efforts on this question. So this is the way to do it, really. Hopefully you're happy with it. Keep going on these challenges. Brilliant.